In this session, we will discuss the sum of an infinite geometric progression. So we have a theorem that states that the sum of an infinite geometric progression whose first term is given by the letter a in lowercase and the common ratio r in lowercase, and also there's a condition for common ratio. That means the absolute value of the common ratio must be less than 1. Then if the sum is given by the first term divided by 1 minus the common ratio r. So let's try to understand this theorem. So we know that the sum, if the first term is a and the common ratio is denoted by r, then the sum to n terms of a geometric progression is given by the formula as n equals to a multiplied to 1 minus r raised to the power of n divided by 1 minus r. So this theorem holds true whenever we have when the absolute value of r less than 1. So what's absolute value of r less than 1 mean? So absolute value of r less than 1, this means that the common ratio must lie between two values, -1 and +1. So in a sense, r could take fractional values, for example, -2/3, -half, +1/4, +half, etc. So this could be the value of r. Then we know that the sum to n terms is given by this particular formula. Now we can rewrite this particular equation as, we can break it down into two parts. So we have a minus a r raised to the power of n divided by 1 minus r, which can be also represented as a over 1 minus r minus a times r raised to the power of n divided by 1 minus r. So this is the formula for Sn. Now let's say we have our n tending to infinity. That means we are considering a very huge value for the total number of terms that can extend up to infinity. Then in that case, since r is less than 1, so that means that if we are raising it to the power of n, then this must go to 0. So for instance, you can think of it like this. So let's say our r value is 1 over 2. So if we square r, then we're going to get 1/4. Now 1 over 4 is less than 1 over 2. If we cube it, then we are going to get 1 over 8. So if we raise it to the power of 10, we get 1 divided by 1024. So we can see that this value is decreasing as our r value, the power of r value increases. So for a very huge value, let's say we take r raised to the power of 1000, this value is going to be so small that it is almost close to 0. Then we can say that when r, so whenever n tends to infinity, then r raised to the power of n tends to 0. So now that we have the value of r raised to the power of n, so we can substitute this value back into this equation. Then we have s infinity, the sum to infinite number of terms. So that's a over 1 minus r minus a times 0 divided by 1 minus r, or we can simply say that our sum to infinite terms of a geometric progression is given by the formula a divided by 1 minus r, with a condition that the common ratio must be, absolute value of the common ratio must be less than 1. So let's try to understand this idea with the help of few illustrations. Problem number 1. We need to obtain the sum to infinity of the given geometric progression. So let's begin. Here we will obtain few of the things that we need for finding out the sum. So that means we need the value of a first term, so that's -5 divided by 4. We also need the value of the common ratio. All we have to do is take the second term and divide it by the first term. So dividing, since our first term is a fraction, so dividing by the first term simply means multiplying it with the reciprocal of the first term. So that will be -4 divided by 5. So 5 times 5, 5 times 1 is 5, 4 times 4 is 16. So we are going to get a common ratio of -1 over 4, which clearly states that the absolute value of r, which will be equals to 1 over 4, so this value is less than 1. Now we know that the sum to infinity, that means sum to infinite terms of the geometric progression, is given by a over 1 minus r, which will be equals to, so we have -5 over 4 divided by 1 minus of -1 over 4, which will be equals to -5 over 4 divided by, in the denominator here we have 1 plus 1 over 4, so that's simply 5 over 4, and this gives us a value of -1. So that means if we add this geometric progression, -5 over 4 plus 5 over 16 minus 5 over 64, then it all sums up to a value of -1 if we consider a very huge number of terms, such a huge number that n almost tends to infinity. So it converges to a value of -1. So let's try out another problem. Problem number 2. We need to obtain the sum to infinity of this given geometric progression. So let's begin. So here, our first term, that's square root of 2 plus 1. Then we need to find out the common ratio. So the common ratio will be 1 divided by, the 1 is the second term here, divided by the first term, which is square root of 2 plus 1. So if we rationalize the denominator, for that we are going to multiply the numerator and the denominator with square root of 2 minus 1. And that means in the denominator we are going to get square root of 2 whole squared minus 1, or simply the value is going to be square root of 2 minus 1. We can also verify if this is the correct common ratio or not. We can take the third term, which is square root of 2 minus 1, and divide it by the first term. So this is also giving us a value square root of 2 minus 1. So this is going to be our common ratio. This value, is it less than 1? Is the absolute value of the common ratio less than 1? That's true, because we know that square root of 2, that's approximately 1.414. The 1.414 minus 1, so that's 0.414, approximately 0.414, and this value is less than 1. Now that we have the value of both the first term as well as the common ratio r, we'll try to find out the sum to infinite terms of a geometric progression, which is given by the first term a divided by the common ratio, which is 1 minus the common ratio is square root of 2 minus 1. This is going to give us square root of 2 plus 1 divided by the 1 minus of square root of 2, positive 1, so that means we have 2 minus square root of 2. So we'll need to rationalize the denominator, but before doing that, so let's take square root of 2 as the common factor in the denominator. So that means this will get multiplied to square root of 2 minus 1. Now we will be rationalizing the denominator. For that, we'll have to multiply both numerator and the denominator with square root of 2 plus 1. So we have square root of 2 plus 1 whole squared in the numerator, whole thing divided by square root of 2 multiplied to square root of 2 minus 1 times square root of 2 plus 1, which will be equals to, so we have 2 plus 2 times square root of 2 plus 1 whole divided by square root of 2 multiplied to square root of 2 whole squared minus 1 squared. This is going to give us 3 plus 2 times square root of 2 divided by square root of 2 multiplied to 2 minus 1. Right. So that means we now have 3 plus 2 times square root of 2 divided by square root of 2. We're then going to multiply both numerator and the denominator with square root of 2 to get rid of the square root in the denominator portion. So we have 3 times square root of 2 plus 4 divided by 2. So that means we now have 2 plus 3 over 2 multiplied to square root of 2. So this is going to be the sum to infinity of the given geometric progression. Moving on to the next problem, we have problem number 3. We need to obtain the sum to infinity of the given geometric progression. So let's begin. First, we'll represent the entire series by S, and we're going to combine all the terms containing multiples of half. That means we have half plus 1 over 2 cubed plus 1 over 2 raised to the power of 5. This goes all the way up to infinity, and this entire sum will be added to the other sum, where we have 1 over 3 squared plus 1 over 3 raised to the power of 4. So here we're considering all the sum that are multiples of 1 over 3 plus 1 over 3 raised to the power of 6. This goes all the way up to infinity. Now we have two geometric progression. In the first geometric progression, so here the first term is half and the common ratio r, so that's 1 over 2 cubed divided by half is going to give us 1 over 2 squared, or simply 1 over 4. Then coming to the next geometric progression, here the first term is 1 over 3 squared, which is 9, and then we have a common ratio 1 over 3 raised to the power of 4 divided by 3 squared. We have 1 over 3 squared, or simply 1 over 9. So let's find out the sum to infinity for each of the two geometric progression. So for the first geometric progression, we have the first term a divided by 1 minus the common ratio 1 over 4, plus for the second geometric progression, we have the first term 1 over 9 and in the denominator we're going to subtract the common ratio from 1. So let's further simplify. So we have 1 over 2 divided by 3 over 4 added to 1 over 9 divided by 8 over 9. So let's further simplify. This is going to give us a value. So we have half divided by 3 over 4. So we have half multiplied to 4 over 3. So 2 times 2 is 4. This is going to give us 2 over 3 added to the 9, and 9 gets cancelled. So we have 1 over 8. So let's combine it. So 3, we have a common denominator of 24. We have 16 plus 3. So our final sum is going to be equals to 19 over 24. So let's move on to the next problem. Problem number 4, we need to obtain the sum to infinity of the given geometric progression. So let's begin. So here, our first term, that's 1. Our common ratio will be, we'll divide the second term by the first term, so we're going to get negative 1 over 3. The sum to infinity of the geometric progression will be 1 divided by 1 minus negative 1 over 3. So we have 1 over 1 plus 1 over 3. So that's going to be 4 over 3. So 1 divided by 4 over 3, it will be 3 over 4. So this is going to be the sum. Let's go to the next problem. Problem number 5. So we need to obtain the sum to infinity of the given geometric progression. So let's begin by first denoting the sum by s. So we have s equals to, we'll rewrite the terms. So rewriting the terms means we will look for the terms that contains the factor 2 over 5. So this is going to be the first term, followed by, here the third term will become the second term, 2 over 5 cubed, because this particular term also has a factor of 2 over 5. We can also predict the value of the third term, and that is going to be 2 divided by 5 raised to the power of 5. So this goes on. Then we will combine all the remaining terms which have a factor of 3 over 5. So we have 3 over 5 squared plus 3 over 5 raised to the power of 4. And we can predict the third term, so that will be 3 over 5 raised to the power of 6. So this goes on. So we have obtained 2 geometric progression, and both of them are infinite series. Now the first term, for the first geometric progression, the first term is 2 over 5, and the common ratio will be equals to, so we have 2 over 5 cubed divided by 2 over 5. That will be 1 over 5 squared, or 1 over 25. In the second case, the first term a will be equals to 3 over 5 squared, so that's 25. The common ratio r will be 3 over 5 raised to the power of 4 divided by the first term, 3 over 5 squared. So we're going to get 1 over 25. So let's find out the sum. So the sum will be, for the first geometric progression, we have 2 over 5 divided by 1 minus 1 over 25 plus 3 over 25 divided by 1 minus 1 over 25. So this total sum, this is going to be, you can perform the calculation, and this is going to give us a value 13 divided by 24. So let's move on to the next problem. Number 6, we need to obtain the sum to infinity of the given geometric progression. So here we have our first term given by 8. The common ratio will be equals to, so we'll take the third term and divide it by the second term, which is 4 times square root of 2, and this is going to give us a value 1 over square root of 2. So 1 over square root of 2, that is approximately 0.707, and this value is less than 1. So that means now we can find out the sum. Our sum will be equals to 8 divided by 1 minus 1 over square root of 2, which means we have 8 times square root of 2 divided by square root of 2 minus 1. We'll need to rationalize the denominator. We're going to multiply both numerator and the denominator with square root of 2 plus 1. So in the denominator, we're simply going to get square root of 2 whole squared minus 1 squared, and this value is going to be equals to 1. So let's simplify the numerator portion. 8 times square root of 2 multiplied to square root of 2. So we have 16. We have 16 plus 8 times square root of 2. So this is going to be the sum of the given geometric progression. Let's move on to the next problem. We need to obtain the value of the given expression. So here we have to first rewrite this expression. We observe here that all the bases are the same, which has a value of 9. So we can add up the exponent. So in the exponent, we're going to have 1 over 3 plus 1 over 9 plus 1 over 27. This goes all the way up to infinity. So here, we'll only tackle with the exponent part first. So let's denote it by the sum s. So we have 1 over 3 plus 1 over 9 plus 1 over 27, and so on. So here, the first term is 1 over 3. The common ratio is 1 over 9 divided by 1 over 3. So that's also 1/3. So our sum is going to be equals to 1 over 3 divided by 1 minus 1 over 3, which will be equals to, so we have 1 over 3 divided by 2/3, which is going to give us a value half. So our sum is half. Now that means our entire expression can be also expressed as 9 raised to the power of 1 half. So the square root of 9, this value is equals to 3. So hence we can say that 9 raised to the power of 1/3 times 9 raised to the power of 1/9 times 9 raised to the power of 1/27. So this product is equals to 3. So let's move on to the next problem. The final problem, problem number 8. So we need to obtain the value of the given expression. So we can rewrite this as 6 raised to the power of, so here we can see that all the bases are the same. So clearly we can add up the exponents. So we have half added to 1 over 4 plus 1 over 8. This goes all the way up to infinity. So let's find out this value. Now we need to obtain this sum. So let us denote it by s. So let s be equals to half plus 1 over 4, which is 2 squared, plus 1 over 8, which is 2 cubed. Now this is a geometric progression with a equals to half and the common ratio r equals to 1 over 2. So that means our sum will be half divided by 1 minus half. So half divided by 1 minus half is simply 1. So that means we have 6 raised to the power of 1, and this is going to be the value of a given expression.